This is a spring. I mean, of course, it's a spring. Why I call it spring? Because you know what is the property of a spring. If you compress, imagine if the spring, if you compress or if you elongate, imagine you are going to apply force in this direction or in this direction. This is now the spring is in the equilibrium position. The spring will move compressed or the spring will elongate. So that means if the spring will move from the equilibrium position. So this is the equilibrium position. So x equal to 0 to this x or to this point. So this is the elongation and here is the compression of the spring. Yeah, you know that. Like every other spring, this is a normal spring, you know. It is very common for you, right? Imagine if this is the spring. I mean, if I apply a force here, if I apply a force, imagine if I'm going to hang a mass here, or if I push this direction, if I, you know, if I pull this direction, okay, this will be moving. It will be, you know, that the spring, imagine if this is the equilibrium position, x equal to 0, that means it is in equilibrium, there is no movement. But if I apply a force here in this direction, what happens? The spring will be elongated. So let me show you that. The spring is elongated, and very bad drawing, no worries. Okay, now the spring is like this. So how much it extended from this equilibrium position? Now the spring is extended to a distance which is we call x. And actually you notice that why the spring extended? Because I applied a force in this direction. So can I ask you a question? If I increase this force, what will happen? What will happen? What will happen if I increase this F? Of course, your answer is correct. The X will increase. The F, as if I increase F, the X will increase. Or you can say F is directly proportional to X. Why? Because as I increase the force, the extension produced the spring is increasing. It's the same thing. As I compress the spring, the extension produce, the compression in the spring also increase. This is the same thing. The spring, maybe you can compress also. Imagine if the spring is in this situation and you have a mass attached, you just push this. So it will be compressed, right? And this is the distance it compressed. And actually, when we talk here, we need to talk about a little bit about, I need to talk a little bit about Hooke's law. What is Hooke's law says? Within the elastic limit, within the elastic limit. Why this? This is a condition within the elastic limit. What is the meaning of elastic limit? I said here, if I increase the force, the extension is going to increase. Is it true for all like force? You know that if I apply force more and more and more, what will happen? The spring will extend and no, the spring will break. So this property only exists in a certain limit of force. So there is a range. I cannot apply too much force on this. So within that force, so or within the elasticity, because with actually if I increase more force, if I apply more force, the spring will damage. Then the spring is, then this will not be a spring. It will be a piece of metal then, right? A metal wire. So there it will never show the property of a spring. Yeah, so that's why I said this is only happening. This F is proportional to X only within the limit of elastic. Within the elastic limit, F is proportional to X. And one more thing, what F here? In fact, the moment when I apply force, there is a force developed in the spring. What force? The spring, because the force that you are applying is called the deforming force. Why we call it deforming force? Because I apply a force to this spring and the spring shape is changed, so deform it. So that's what we call the deforming force. But you know that even though the spring shape is deformed, the moment you remove your force, the spring will go back to its original condition. its equilibrium condition, its normal condition. Why? Since there is a force inside the spring, we call that force is called restoring force. The force in the spring, the natural force in the spring due to their molecules or the material or the geometry of the spring, we call it restoring force, right? So what happens here? We know that the deforming force and the restoring force are equal, but they are at opposite. Now look at this. We are talking about the restoring force. Here the restoring force and the deforming force are in equal in magnitude, but within the elastic limit. But the restoring force, imagine if the deforming force is in this direction, the restoring force will be in this direction in the spring. So look at the spring, the restoring force and the extension produced. Here the extension is in this direction. So are they in the same direction? No. So we can say that this F is directly proportional to minus X. And actually we know that this is true for all spring irrespective of the hardness of the spring, because you know that the springs are available with a different size, different hardness, because the spring that we use in our car, airplane, train, all are very strong pin and strong spring. Also you use springs in your pen, right? In your pen, most in your watch. All these are very light spring. Okay, the lightness or hardness of a spring is given in terms of this constant. That is what we call the spring constant. So F is directly proportional to X and F is equal to minus Kx, where K is a constant called spring constant. Where K is a constant. So for the simplicity, we are not going to bother about the direction of restoring force and K. We're just going to simply take on this equation as F is equal to Kx. So we understand that the force on the spring is, if we increase the force on the spring, the extension is also increasing, or the compression is also increasing. So we can say F is directly proportional to X, or F is equal to Kx, where K is a constant we call spring constant. And you understand that for all spring, for every spring, this is true. As you increase the force, the extension or the compression will increase, whether it is a light spring or a hard spring or a heavy spring. This is true. So this is true for all the spring. Then here comes the new thing that we call the constant K. So K equal to F divided by X. So that means if K is big, if the K value is big, means imagine K is 800. Yeah, what is the unit? Newton per meter. Oh, K is 800 Newton per meter. That means this is a heavy spring. Maybe K can be 2 Newton per meter. So that means it's a, or maybe less, K can be 0.02 meter, Newton per meter. So these are light spring, these are heavy spring. Anyway, our